Before the 19th century, space and time were thought of as two separate entities, space and time. Einstein unified these two ideas into one continuum called space-time. If you're a person standing still and a car drives past you, then they appear to be moving forwards. However, if you're the person sitting in the car, then from your point of view, it's not the car that's moving forward, it's the person standing still who's moving backwards. Now imagine there's a person who's running beside the person who's standing still, and the car drives past them both. From the person who's running point of view, the car appears to be going slower than for the person who's standing still. If a photon, a particle of light, travels between the person standing still and the person in the car from point A to point B, then common sense would say that for the person in the car, the photon would appear to be moving slower than for the person standing still, but this is not the case. No matter how hard we've tried, we've always measured light as a constant speed, approximately 300 million meters per second. For every clock, there needs to be something that makes it tick forwards. You can use cogs, pendulums. The most accurate clocks are made out of atomic particles. For this example, we're going to use a light clock. This works by two mirrors bouncing the light back and forth. Every time the light hits the mirrors, the clock ticks on. Imagine one of these clocks is inside this rocket. When the rocket is standing still, the light only has to go from point X to point Y. When the rocket starts to move, the light has a further distance to travel to keep up with the rocket. And yet, because light is a constant speed, the light does not speed up. So something has to give. The thing that gives isn't light, but time itself. This theory was proved in 1971 when they flew an atomic clock around the world and compared to one that had stayed on the ground. Before the clock was flown, the two clocks measured the same time. When it had landed, the clock was fractions behind the other one. Space-time isn't completely straight as you might think. It actually bends. The thing that makes it bend is gravity. Now let's take a look at Newton's formula for gravity. He said that F equals G by m1 by m2 divided by r squared. Now what this actually means is the force of gravity equals the gravitational constant, which is 6.67408 by 10 to the minus 11, times the mass of the first object times the mass of the second object divided by the distance between them squared. The thing that affects the curvature of space-time is gravity. The theory we're going to look at the moment is called the equivalence theory. If there's a box in outer space travelling at the speed n and a box on Earth with a gravitational pull of n, you shouldn't be able to tell the difference between them. So if the box in space travelling at speed n has a photon of light travelling through it from point X to point Y, then say the photon starts somewhere around here at the top of the box. Then by the time it gets to the middle of the box, it'll have moved down in the box because the box will also be moving upwards. And by the time it's at the other end of the box, the photon will be somewhere around here at the very bottom. So if we were to look at that in one image, then it would look something like this. So that's a box travelling through space. So if we apply the theory that a box travelling through space at speed n and a box travelling with no speed on Earth with a gravitational pull of n is the same, then a box on Earth will also look something like this. Einstein knew that this theory was wrong because a photon has no mass, and therefore if this formula was correct, then gravity could not act upon it. Another reason why Einstein knew this theory was wrong was because this would make gravity instantaneous, and Einstein knew that nothing was faster than the speed of light, and not even the speed of light is instantaneous. The theory that Einstein came up with was that mass physically bends space-time. This makes curvature of space-time. It's kind of like if I was on a trampoline and you placed balls at the edge, they would all roll towards me. This would mean that if the sun evaporated, the planets would immediately exit their orbits, but this is not the case. This is the formula that Einstein came up with. Unfortunately, due to the time limit on this video, I don't have time to fully evaluate this problem, but I'm just going to give you a bit of background information on it, and maybe some of you would like to research it yourselves. This is called Einstein's field equations. It might look like just one equation, but in fact, it's 16 equations. However, 6 of these equations are just duplicates, so there's only 10 equations. What this formula basically means is that mass tells spacetime how to curve, and curved spacetime tells mass how to move. The left-hand side of this equation basically talks about curvature of spacetime, whereas the right-hand side talks about mass and energy.